Recording is rolling. It is Thursday, October 3rd. We're gonna knock out these textbook puzzles today. So here, for context, so far we've done most of them from law of inertia. We did a bunch of these for the Newton's second law of motion. Guys, today we're gonna, guys, everybody look up here. Everybody's got paper out, ready to go? Right. We're gonna do some from Newton's third law. Now, I put probably way too many questions on this page, so just whatever we've done in class is all that I'm gonna count. Okay, so if you've been doing all of them, then follow along. Everything we've done in class and plus the ones we're about to do today. Guys, if you want to turn these in today and get them off your hands, you can. I'll give you full credit for just doing it. Everything we did in class. If you need a few extra days, it's okay too. Guys, the end of the class today, I'll get you guys your next take-home quiz, which is going to be on this type content. Right, so forces dynamics. Tomorrow, my plan is to do Varanon frame with you guys. So real fast, I do have a poster for this one. This is how can you determine the optimal location of a factory based on transportation costs. Right, there's a physics solution to that involves dynamics. So that's tomorrow's plan, your lab activity. Guys, what's coming up on Wednesday? What's coming up this coming Wednesday? PSAT. Hey guys, here's the deal with PSAT. Is if you are in 10th grade, then the school's ordered one for you, an exam for you. You're going to be taking it if you're in 10th grade. Also, there's a few 11th graders taking it. I have an Excel file that says everybody in the whole school is taking it and where they're supposed to be testing. Yeah. Anybody who's taking PSAT, guys, PSAT, which is, again, mostly 10th graders, but maybe a handful from other classes too. Guys, if you have a question about where you're testing, ask me the last 5 minutes of class. I'm going to save the last 5 minutes of class for giving you guys your take-home quiz and asking any questions about where you're testing PSAT. Right. Now, if you're not taking PSAT, which is probably most of you guys, then are you going to show up to this class anyway on Wednesday?
No.
No, because, guys, what's going on in this classroom? Guys, listen up here. So you know what's going on. What's going on? Guys, everybody, look up here.
They're testing.
Guys,
I'm already taking that thing.
Okay, guys,
Cool.
Great. This still applies to you. You're still not coming to this class on Wednesday because they're testing in this classroom. They're going to be testing here all day. So where are you guys going on Wednesday? Where are you going on Wednesday? Media Center. Media Center? Okay. Media Center on Wednesday. All right. All right, so now puzzle time. Puzzle time. Let's pull up your puzzles. Again, just whatever ones we've done in class and we're going to do right here today is all I'm going to count. So see what looks fun and exciting. Here, let's start with number 10. See, what is this? Earth pulls down on you with the gravitational force you call your weight. Do you pull up on the Earth with the same amount of force?
Yes.
So number 10, you're saying yes? You're saying yes? Yeah, let's do a diagram for that. Number 10. Okay, here's the Earth, here's you. So is the Earth pulling down on you with some weight? Let's say it's like 500 newtons, for example. Okay. And are you also pulling up on Earth? With how much force? The same force. The same force. Is that Newton's third law of motion? Right. Okay. Now, there's also a normal force that I left out. Is the normal force holding this person up?
Yeah.
Yeah. Is the normal force also pushing down on the floor and holding the Earth back in check?
Yeah.
Yeah. So nothing's really moving. Right. I left those forces off. It's the same force. So yes, same force. All right. Let's skip down to some that have pictures. Those look pretty fun. Number 79, or sorry, 49. I always said it. 49. The strongman. Oh, look, we got a strongman here. Will push the two initially stationary freight carts of equal mass. Ooh. All right. So maybe it's like, oh, I don't know, 1,000 kilograms, something like that, apart before he himself drops straight to the ground. Is it possible for him to give either of the carts a greater speed than the other? Why or why not? What do you guys think? Yes or no?
Is it like, is he applying equal like force to them, or we don't know?
Does it have to be equal and opposite forces? Does it have to be equal and opposite forces?
Yes.
It's Newton's third law of motion, doesn't it?
Yes.
Ah, okay. So 49. Here's 49. Here, you guys can write it as I'm writing it. I'm going to say the carts will have the same speed Yeah, I gotta shut this off. Here we go. Right. Surprise noise. Parts will have the same speed because it's the same force. Newton's third law. So the third law of Newton's third law of motion. Let's call it third law. On each cart of equal mass. Because it's the same force for the same mass that is going to result in the same what? Starts with an A. Acceleration. If you apply the same acceleration for the same time, for the same time, that goes back to kinematic motion. That's going to result in the same final velocity. There you go. All right. So yeah, I know that's really wordy looking, but in the equations it looks like this. Acceleration is force on mass. It's the same force on the same mass, therefore it's the same acceleration. The speed it picks up to is just acceleration times time. Boom, boom. So there's the equations. Yeah. Oh, teaching many years. Yeah. A little arrow. It's like a little arrow. Like one idea leads to another idea. All right. But look at number 50. Number 50. This looks kind of similar. Got a spring here. Here, guys, focus here. Two carts, but now the masses are different. We got M and 2M, and they fly apart when compressed. What is the acceleration of the heavy cart compared to the light cart as they move apart? Ooh. Yeah, number 50. Yeah, number 49, everything was the same. Same force on the cart, same mass, the same acceleration. It was for the same time interval, same speed. Right? But number 50, I think it's going to be different. Here, guys, let's do a numerical value. Let's say M is 1,000 kilogram. Spring. And then 2M would be how much? 2,000 kilogram. Right. Now, guys, Newton's third law of motion. Does the spring push left on this mass equal force to right on this mass?
No.
For every force, there's an equal and opposite reactive force? Because it's the same force both ways. It's the same force. Okay. Now the resulting motions are going to be different because the masses are different, but it's the same force. Right? Let's make up a force. You guys want to make up a force?
No. Oh yeah.
All right. Say, here, guys, are you guys writing this down? You guys got paper? Here, you have to get you guys paper? Paper. Yeah, I know. All right. Everybody's got paper now. Give you guys all the answers. Let's make up a force. Suppose force equals 1,000 newtons. Would this force also be 1,000 newtons? Has to be. Now that's Newton's third law of motion. Right? That's why it's in this chapter. Right? It has to be equal and opposite forces. Right? So let's see, what is the acceleration of the small cart? Acceleration of the small cart is force on mass of the small cart. Acceleration of the large cart. Yep. Now it's the same force, but on a different mass. Like that?
What's under the A?
A small, A large. M small, M large. So small, large. Okay. So a subscript usually like names the variable, like points to a specific object we're looking at. Right. Now we made up some numerical values. We could have made up any numbers as long as they meet the conditions. Okay. Let's see what it is. So acceleration for the small cart is, I got 1,000 Newton force acting on 1,000 kilogram, which is equal to what? One what?
Meter per second squared.
Meter per second squared. That's it. Okay. But for the large cart, okay, now it's the same force, has to be the same force. Now it's on a larger mass. That's equal to what?
I found.
A half of a meter per second squared?
Ah.
Now, the actual question was, they said a ratio. Yeah, the acceleration of the heavy cart compared to the light cart. Like, what's the ratio? So if I do acceleration of the large cart divided by acceleration of the small cart, this is really how the book framed the question.
This is.
That's going to be a what to what ratio.
One to two.
There you go, just like that. All right.
Same thing. Same book.
All right, that's good. Let's do, yeah, we'll just go down, hit the pictures. I think it's pretty good. So number 52, 52. We got, wait, is that these people? Oh, never mind. Hold on. What is this? Here. What is 52? I started on 52 anyway. They're astronauts. That looks fun anyway. Let's go ahead and do 52. I see. It's talking about astronauts. Floating some distance apart in space. They are joined by a safety cord whose ends are tied around their waist.
Oh my god. Sorry.
Right there.
I was so-
All right, so two astronauts, safety cord tied together. Ken starts pulling on the cord. He pulls Joanne toward him. Or will he pull toward Joanne? Or will both astronauts move? What do you guys think? So I'll draw this up. 52. 52. Can you guys draw a couple of astronauts?
Yeah. You can't join astronaut.
What number is it?
There, 52. A couple of astronauts. And they are, here's Ken, here's Joanne. And they got a rope between them.
She should have named Barbie.
Well,
What's that?
go. Right. And they're just, guys, they're just floating around in space, right? Just floating around in space, right? Then Ken starts to tug on this rope, right? And let's say, even though they're floating in space, maybe it's like relative to some nearby space shuttle or something. Maybe we got like a shuttle over here or something, right? Like that, right? Right. So we're saying like, what's their speed relative to the shuttle, right? So now Ken's doing all the pulling, guys. Ken's doing all the pulling, right? Does only Joanne move toward him? Does only he move toward Joanne? Or do they move toward each other? Huh? Guys, when Ken pulls on the rope, does Joanne feel a tension pulling this way? T tension? Does Ken also feel a tension?
Yes. Yeah.
Which tension is bigger?
They're equal.
They're equal. It's the same tension. Same tension. Right? Now, if they have different masses, do you think they're going to move the same?
Yes.
Yeah.
Oh wait.
Okay.
No.
Right. Okay. Yeah. If guys,
Same mass.
yeah. If they're the same mass, they'll both move the same. If they're different masses, they'll move different.
Yeah.
But regardless, do they both move
Yes.
toward each other?
Yeah.
So if you're looking out the window of this spaceship here, you'll see Ken move to the right, Joanne move to the left, like relative to the ship. All right, 56. Two people. Of equal mass. Equal mass. That's nice. Attempt a tug of war with a 12-meter rope standing on frictionless ice. Actually, this sounds really similar to what we just did, isn't it? Frictionless ice. Your normal force cancel out. There's no friction forces. Sort of being in space, kind of. Right? Similar type motion. When they pull on the rope, each of them slides toward the other. Wait, what? Is that it? Oh, there must have been more to that question. Oops. Okay, never mind. We're gonna keep going. I guess there was a question that got cut off there. Number 76. 76 time. 200 Newton weights. Attached is shown. 100 newtons, 100 newtons. Does what does the spring scale read?
200.
Let's draw this out. Yeah, I'm gonna draw this out. What you guys thinking of it? Thinking about it. Number 76. We got got a weight here. Where's my ruler? Got a weight here. Oh, pulley, rope, something like that. Oh, oops, we got a spring scale in the middle.
Oh my God. Blame our snake.
What?
Something like that. All right, so I know that this block weighs 100 newtons. This one also weighs 100 newtons. There's the setup.
No, wait, I'm not.
All right, let's go through this methodically. So guys, what's the tension in this string pulling up right here?
Like 2 weeks ago. Or like 1 week ago.
What's this tension equal to?
Yeah, I'm gonna ask you.
100 newtons. Oh yeah. What's this tension equal to? 100 newtons. Guys, what's the tension? What's the tension right here? 100 newtons.
Yeah.
Guys, put your phones away. Look up here. Trying to help you guys out. What's the force rating on the spring scale?
200. 300.
Is the force the same as the tension?
Yeah.
You guys just told me the tension here is 100 newtons. How about 100 newtons? Oh yeah, 100 newtons right there. There's just 100 newtons.
I would point out.
All right. Let's do number 67. I got a stone is at rest. Oh, look at that. You guys see that big blocky looking stone? Big square looking stone? Is it rest? And okay, then we got this this rolly looking stone. I guess everything's just at rest. Identify all the forces on the stone and draw the vectors. Show that the net force on the stone is 0. Okay, number 67 we're gonna do. Yeah, let's go do that. Number 67. So we got an incline. There's like a big block right here that's just holding everything in place. We got this rolly looking stone. We're focused on the rolly looking stone. Okay? And it's not moving, it's at rest. There's some angle here. This could be whatever angle. Make up a number, just call it theta in general. Something like that. Yeah, well, the ruler helps. You guys got ruler? Yeah, ruler helps. All right. All right, guys, this stone, what's one force on this stone?
MG.
Yeah, mg. Pull straight down. Mg. Right. Yeah, let's do some numbers. How about that? I'm going to call this angle 37 degrees. And I'm going to call the weight equal to 100 newtons. I'm just going to make something up. Okay. All right. Suppose I did that. All right, guys, what's another force on this stone? What force is supporting from the surface?
Force.
The normal force. And that points, okay, normal to the surface being perpendicular. That'd be like that way about. Call us Fn from the surface. Okay. And then, do you guys think this block also pushes back with also a normal force? Do you guys think? Normal force? All right, so I'm going to draw a force this way and say this is normal force from the block. Okay, just like that. I guess this just should be incline and block. So like that. All right, let's get some numerical values because I got some numbers on the board. Can you guys break this weight into components just like this? That weight is trying to push the boulder into the surface and also trying to make it roll along the surface. There's my two components. Guys, what is this angle right here? If this was 37 degrees. Yep. 37 degrees. Okay. All right. Now, if you know the full weight is 100 newtons, and this angle is 37 degrees, who can tell me what is this component right here?
Which one?
27.
This right here.
26 degrees.
Take 100 newton. Well, it's in newtons.
Oh.
Take how many newtons?
That's what I.
Multiply by
74.
sine sine
Oh.
of 37 degrees. And guys, there's a reason I picked 37 degrees. Why did I pick up 37 degrees? Guys, anytime you see 37 degrees, I'm setting up a what triangle?
3, 4, 5.
3, 4, 5. Guys, watch this. 100 sine 37. It's 60 newtons. 60 newtons. Guys, see that's 3/5 compared to the full weight, right? Guys, if that's 3/5 of the weight, what do you think this component is? 4/5 of the weight? mg cosine theta, that's 100 newtons. Cosine 37 degrees is going to be 80 newtons. Right? Guys, if this component's 80 newtons, what is this normal force from the incline equal to? 80 newtons. And what is the normal force from the block equal to?
40.
60 newtons, because it cancels out with this one right here. This 60 and this 60 cancel out. This 80 and this 80 cancel out. So your guiding principle is the sum of forces is 0 newtons. That's true in the x direction. That's also true in the y direction. And my xy axis, I'm thinking about a Cartesian system aligned to the surface. Here's a little thought cloud here. It's my guiding principle right there.
Sigma.
Shut up.
That's it.
You just said it.
Well, yeah, I know. You're a hypocrite.
You're such a hypocrite.
No, you don't.
All right. Let's do number 62. Oh, yeah, sorry, these are a little bit out of order. Oops. 62. I've got a stone suspended at rest by a string. Draw force vectors for all the forces acting on the stone. All right. All right, and then should the forces zero out. So stone, string, ceiling, 62. 62. Guys, what's this force called?
MG.
MG. What's this force called?
FN.
About tension. Guys, it's a string. String has tension. Okay. Guys, a normal force, normal means perpendicular, as in like a surface acting force. FT is the force due to tension, like a tension force.
It's a FaceTime.
Yeah. So are those, guys, do those zero out? The sum of forces is 0 newtons. All right, number 63. The same stone is being accelerated vertically upward. Draw the force vectors. Oh, wait, same stone. That. Okay, so it's on a string. Okay, but it's being accelerated upward. Okay, I think this was a mini lab that you guys did a few weeks back. Okay, so that means the sum of. So the sum of, like if you add all the forces together, you see, like if this is 20 newtons up and this is 20 newtons down, 20 plus negative 20 is equal to 0. Yeah, right that. Sum of. All right, so now let's get another stone. String. Because this one's gonna accelerate up. Right now, maybe it's moving up faster. Maybe it's actually moving down, but still accelerating up. They slow down to stop moving down. Right. Either way, it's got two forces on it. Here's the weight pulling down, mg. Right. Guys, how does the tension in the string compare to the weight?
Stop.
What'd you say?
Guys, if it's accelerating up, you guys know net force is equal to mass times acceleration. Right, you guys remember this? So if it's accelerating up, which way is the net force?
Down. Oh,
Huh?
wait.
Up,
Oh, yeah.
up. So how's the tension compared to the weight? It's more than. Guys see that vector is more than that vector?
More than.
So that, here, I'll give you guys an example. Maybe the last question was like 20 newtons and 20 newtons. Maybe this one's like 30 newtons versus 20 newtons. It's not like that,
It's on that side.
but it's bigger, right?
It's on that.
All right.
Was this 63? EF equals.
Yeah, 63.
I looked at your.
Oh, wait, no.
I honestly.
Yeah.
All right, guys, we're gonna do one more. You guys ready for the last one? Last one, number 80. Number 80. Number 80.
It's sigma equals 1. And then.
I got strongman can withstand the tension exerted by 2 horses pulling in opposite directions. How would the tension compare if it was only 1 horse versus a tree? How would it compare if it was 2 horses versus a tree? Let's do all those scenarios for number 80.
That's not my fault. Whoopsie.
Let's see. Guys, draw a strong man. Guys, draw a strong man.
Yes.
All right, you guys draw that. Guys, draw a horse.
That's a good one. That's such a good one.
Ah, well, thank you. Horse.
Art teacher.
I like physics.
There's my horse. So, yeah, you just say. It's fun.
Those are caveman paintings, bro. That's already. It's a horse, trust. Bro, it's a horse.
All right. Hey, let's put some numbers on the board. Let's get some numbers. How hard do you think a horse could pull? Maybe.
A lot. 1,000.
80 horsepower.
Guys, what do you think your mass is in kilograms about? Maybe about 50, 60 kilograms.
How do you draw so well, Mr.
Do you think you weigh maybe 500 or 600 newtons? Maybe about.
Yeah.
Do you think a horse could probably pull harder than that?
Yes.
Okay. Here, let's go 1,000 newtons. 1,000 newtons. All right. We're just making something up. How hard is this horse pulling to the left?
1,000.
1,000 newtons. Hey. 1,000 newtons. How hard is this horse pulling?
1,000.
1,000 newtons. Hey. How hard is this tree pulling?
Nothing.
Huh?
1,000. 1,000.
1,000 newtons.
What?
Right. Do you think because what the horse keeps pulling, could it eventually pull the tree over? Because there's a tension pulling back on the tree too. But because these 2 forces are from the strong man's point of view. Horse to the right, tree to the left. You could also go from the tree's point of view. And from the tree's point of view, the rope's pulling to the right, and the tree is like planted into the ground, pulling back to the left. Also, with 1,000 newtons. Huh?
Is he floating on the third?
He might be. He might be. Yeah, a little bit. Hey, guys, what's the total tension with 2 horses?
2,000.
2,000 newtons. How much is the tree pulling back?
1,000. 2,000.
2,000 newtons.
Yeah.
Guys say something like that. All right, there you go. So, oh, good. We have a little bit of class time. Here's what I'm going to do is I'm going to roll a few Paul Hewitt videos. I'm going to get you guys your take-home quiz. And also, if I'll pull up that Excel file and see if I see numbers for 10th graders especially. All right. And then Okay, guys, that's all the puzzles we're gonna do. Just the ones we did in class. You guys can turn into the gray tray is all right.